In this video, we're going to be taking a look at how to find the area bounded between two curves. So we've looked at integrals to find the area between a curve and the x-axis, right? So the region that we would see above the x-axis and under f of x here. But we haven't been able to, or haven't looked at, finding the area between two curves. So this region here, which they call S, which is bound between y equals f of x and y equals g of x, and is in between the lines x equals a and x equals b, is often something that we try and find in calculus. Now, we could estimate their area in the same way that we did with our original integral by using rectangles and trying to approximate the area by finding the area of the sum of the area of these rectangles. And if you're trying to find the area of this rectangle, right, the height of this rectangle is going to be the y value here of this function minus the y value here of this function, right? Because that's how you find the distance between 2 points vertically. And so you could just take their difference, and then we would multiply by the width of our rectangle, which is just going to be some delta x. And that would be the area of a typical rectangle if we were approximating using rectangles. Now, in order to find the exact area, what we would do is we would use limits to make the width of the delta x as small as possible, right? And basically we would be using infinitely many rectangles to give us this region. So if I want to find the area of a region between two curves, this is kind of the formula or the integral that we will be using. So we want to know if f and g are continuous functions and f of x is greater than or equal to g of x. So f and g are continuous, and then f is greater than or equal to g of x for all values of x on some closed interval. Then we can find the area bounded between those curves by doing this integral. So we'd say the area from a to b. So remember, it's stuck in between x equals a and x equals b. So we're going from a to b of f of x minus g of x, and then integrating this with respect to x. So basically what you're looking at, what this looks like, is it's just the top function minus the bottom function. So you look at the curve that's on top, the curve that's on bottom, you subtract their y values, or the function itself, right? So it's the function minus the other function, and then you integrate from a to b on this. All right, so let's go ahead and take a look at some examples of this. So in this example, it's asking us to find the area of the region between y equals secant squared x, so that's our first function, and y equals the sine of x. So those are the two functions that we're using. And then the x bounds are from 0 to pi over 4. So essentially, we would have to graph our region here, and we're looking at this from 0 to pi over 4. So let's go ahead and sketch the graph of this. There's my sketch, beautiful computer-aided sketch. So this is my secant squared function, and then this here is my sine function. And you can see that we are bound between 0 and pi over 4. So this region here in green is the region that we're trying to find the area for. Now, in doing this integration, we're integrating with respect to x because you can imagine we're like stacking rectangles kind of going like this way. And so basically what's happening is we're accumulating area along the x-axis, right? We're moving from left to right, accumulating area along the x-axis. And so that's going to be an integration with respect to x. So when you integrate with respect to x, it's going to be the integral from 0 to pi over 4, 0 to pi over 4. And remember, it's going to be the top function. So in this case, the top function is the secant squared. So secant squared x minus the bottom function, which is the sine of x. And then again, we're integrating with respect to x. So go ahead and take the antiderivative. So I know the antiderivative of secant squared is the tangent. The antiderivative of sine is the opposite of cosine, but since it's negative, we're going to be adding cosine of x here. And we're going to be evaluating this from 0 to pi over 4. Okay, so the tangent at pi over 4 is 1. The cosine at pi over 4, that's the square root of 2 over 2. And then minus, the tangent at 0 is 0, and the cosine at 0 is positive 1. But because we have this difference here, it's going to be a negative 1 and the positive 1 that will cancel. So we're just going to get the square root, we're going to get the square root of 2 over 2 is going to be the value of the area bound between these two curves. Okay. So in this next example, we are looking at the area of the region enclosed between the parabola y equals x squared minus 1 and then the line y equals x plus 1. Now you might notice that it is not giving us x values that we are taking the integral in between. And I'm guessing what that means is that we have an entirely enclosed region in between these two curves. So we have to figure out kind of where these intersect, and then we can use those values to try and integrate this. So basically what we want is we want to know where these are equal. So you would set the x's equal to each other. So it's x squared minus 1 equals x plus 1. And then basically solve this like you would with any other quadratic. So I'm going to subtract these things over. So we're going to have x squared minus x minus 2 equals 0, and then factor to solve. So x plus 1, x minus 2. So we're going to get that it's going to be x equaling negative 1 and x equaling 2. So we're going to basically be looking at x values from negative 1 to 2. So if we were to graph this, so let's go ahead and graph this. There you go, my beautiful graph. Again, we said from x equaling negative 1 to 2, right? Those were the solutions or the points of intersection, which we can see here at negative 1 and then at 2. If we plug 2 in, what do we get? 2 plus 1, that's 3. So this point here is 2, 3. And then this point here is negative 1, 0. So we want to integrate this with respect to x, right? Because we're basically going to be stacking our rectangles this way here. So if we're going to do this integral, so we're integrating from, so you can see like this entire region is enclosed between these two curves. So we don't have to specify specific x values. Now that's not to say that we couldn't, right? Maybe we just wanted to know like the area between here and here. So you could do that. If we wanted to just know this area, you just go from 0 to 1. But in this case, they want the entire region enclosed by these two curves. So we're going to go from negative 1 to 2. Remember, we do top minus bottom. So in this case, the top function is x plus 1. So x plus 1. And then we subtract the bottom function, which is x squared minus 1. And we integrate with respect to x here. Okay, so we can distribute the negative through. That's going to be negative x squared plus 1. So it's the integral from negative 1 to 1 of, negative 1 to 2, of negative x squared plus x. Then since this is going to be a positive 1, that's going to be plus 2. And then all with respect to x. All right, so antiderivative. So that's going to be negative x cubed over 3. That's going to be x squared over 2. And that will be 2x. And evaluated from negative 1 to 2. So go ahead and evaluate this, and what do we get? So plugging in 2, that's going to be negative 8/3. That's going to be 2. That's going to be 4. So that's the upper limit. Plugging in the lower limit of integration is going to give me positive 1/3. Negative 1 squared is 1, so that's going to be plus a half. And then minus 2 here. And then once you do all of the arithmetic on this, what do you end up with? I think you end up with 9 over 2. So you get 9 halves after doing all of the sums in this. So you get that the area in between this is going to be 9 halves units. Okay. So in this next example, we're going to look at multiple ways to find the same area. So the region, we're trying to find the area of some region, but we're going to do a few different approaches. So we're going to integrate with respect to x. We're going to integrate with respect to y. And we're also going to use some geometric formulas to help us integrate this. So in this first example, we're finding the area of the region. Again, notice it's just in the first quadrant. This one is saying we just want the area in the first quadrant. Our first function is y equals the square root of x. It's bounded below by the x-axis. That's the whole first quadrant thing. And then the line y equals x minus 2. So let's go ahead and graph all of this. So we'll graph the square root function and graph this line. And when you do that, we get this. So here's our square root function. Here's our line. So remember, we're just looking for the area in the first quadrant here. So that's why it cuts off here, and we are not taking the area in this part here. Okay, so we're just looking for this area of this region right now. So part A is saying find the area with respect to x. Now, when doing this, if I do top minus bottom, the top function here is the square root. Bottom is x minus 2. But initially, bottom is not x minus 2. Initially, the bottom is just the x-axis. And if you recall, right, that's just finding the area between the curve and the x-axis. That's just a normal integral. So we use just a normal integral of the square root until when? When is it that we start having to deal with the second function? Well, that's up until we get to here at x equals 2. So we really have an integral from 0 to 2 of just the square root of x. So that's the first part. So that's this first region here. And then the second region is the integral from 2 to the point of intersection, which is going to be 4 here. And so this part here, now we have to start thinking about top minus bottom. So we're adding the integral from 2 to 4. So the top function here is the square root. So it's the square root of x. And then the bottom function is this line. So it's minus this x minus 2 here. All right. And then we're integrating again with respect to x because we are basically taking accumulating area from left to right along the x-axis. Okay. So antiderivative of this. We can think of this as x to the negative 1/2 here. Or sorry, not negative, positive 1/2. So x to the 1/2. So antiderivative, so add 1, so that's going to be 3/2. So x to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So it's 2/3 x to the 3/2. And then we're adding to that this antiderivative. We can distribute the negative in here, so it'd be negative x plus 2. So that's going to be, again, and this one is evaluated from 0 to 2. From 0 to 2. And then we're adding antiderivative of this. It's the same as this thing here. So it's 2/3 x to the 3/2. And then antiderivative of negative x is going to be negative x squared over 2. And then antiderivative of 2 is going to be 2x. And this one is evaluated from 2 to 4. All right, so let's go ahead and evaluate this. So plugging in 2, so 2 cubed is 8, and the square root of 8, that's just the square root of 8. So we have 2 square root of 8 over 3. Plugging in 0, so that whole thing is going to be 0. So that's our first value. So it's 2 square root 8 over 3. That's the area between 0 to 2. And then we're going to add to this. So plugging in 4. 4 cubed is 64. Square root of 64 is 8. 8 times 2 is 16. So that's 16/3. 4 squared is 16 over 2. That's 8. So minus 8. And then plus 8. And then minus, plugging in 2. We saw that here. So that was 2 rad 8 over 3. 2 squared is 4 over 2 is 2. And then plus 4. Okay, so we're subtracting all of these. So let's go ahead and just distribute the negative through and kind of get rid of some of these parentheses here. So distribute the negative through. That's going to make that negative, that positive, and it's going to make this negative here. So it's going to be negative 4. We can get rid of these parentheses here as well. Now the positive 8 and negative 8 are going to cancel. This 2 rad 8 over 3 is going to cancel with this negative 2 rad 8 over 3. And if you add all this stuff together, what do you get? Well, you're going to get 16 thirds and then minus 2. So 16 thirds minus 2, which is 6 thirds, which is 10 thirds. So this region, the area of that region, is 10 thirds. So that's what we have here. So this region has an area of 10 thirds. All right, so now, what if we wanted to integrate this with respect to y? So integrating with respect to y is a little bit different, right? Our integral, our area formula that we had before, it was the integral from a to b of f of x minus g of x with respect to x, right? And we were integrating with respect to x. But now we're integrating with respect to y. If I'm going to integrate with respect to y, that means my functions have to be in terms of y, right? So now we should be looking at functions of y. So all of our variables need to be in y here. Now, if I'm doing this with respect to y, I'm no longer taking top minus bottom, but instead it's going to be right minus left. Because when we did top minus bottom, it was the larger y value minus the smaller y value. So when we're integrating with respect to y, it's going to be the larger x value minus the smaller x value. So this would be right minus left here. Okay? So the first thing that we need to do, though, is we need to rewrite all of our functions in terms of y, right? So an x equals y. So to get x by itself here, I'd square both sides. So I'd get that x is equal to y squared. To get x by itself here, I just would add 2. So this is going to be x equals y plus 2. So those are my two functions. So the red one is what we have here. Let's make it red, actually. So let's go ahead and do that. So this is going to be this red here. This one is blue. Let's go ahead and make it blue. Sure. So we have those two functions there. So if I'm doing right minus left, so this is going to be the integral from, so now in this case, we're stacking with respect to y. So we're doing our rectangles like this now, right? So we're accumulating area with respect to y. So we're stacking up like this. So we're going from the y value of 0 to the y value up here, which is 2. And then the right function is this y plus 2. And then the left function is y squared. So we subtract the left function and we integrate with respect to y. So antiderivative of this, that's going to be y squared over 2 plus 2y minus y cubed over 3. And we're evaluating this from 0 to 2. So if you go through and you plug all this in, 2 squared is 4 over 2 is 2. So it's 2 plus 4 minus 2 cubed is 8, 8 thirds. So 6 minus 8 thirds. So 6 times 3, that's 18 minus 8 thirds, which again, we get 10 thirds. So exactly what we would expect. And so this is how you integrate with respect to y. So it's going to be the right side minus the left side. And then your values that you use go from 0 to 2, right? You're using the y values instead of using the x values. Okay. How would we do this geometrically? Well, geometrically, basically, we could think of this as just being the integral of the square root function, right? Because we can see that we have just in the first quadrant. So if I were to kind of think about this area here as well, right? If I just took the integral from 0 to 4, that would give me the area of all of that space plus this here, right? Plus this little region there. So if I just do the integral from 0 to 4 of the square root of x with respect to x, I could just subtract this, right? I could just subtract this area that I have here in yellow. Well, what is this region here in yellow? Since we have a straight line here, this is really just a triangle. So the area of this triangle, its base is 2, its height is 2. So it's going to be 1/2 base times height. So half of 4 is going to be 2. So basically we would be subtracting 2 from this integral. So let's go ahead and do that. So antiderivative of x, square root of x, remember this is x to the 1/2. So that was 2/3 x to the 3/2. And this 2 is outside of the integral, so the whole integral is what we would evaluate first, and then we would subtract the 2. So it's going to be from 0 to 4, and then we would subtract 2 from this. 4 cubed is 64, square root of 64 is 8, so that's 16 over 3. Plugging in 0, that's going to be 0, so it's 16 over 3 minus 2, which is 6 over 3, so that again gives us 10/3. So we got 10/3 in all of these, right? So there's 3 different ways that we could evaluate this integral. And the method that you use is really kind of dependent on the functions that you're given. So for this last example, we actually aren't going to be evaluating this integral. We just want to figure out what is the best method to use. Do I want to integrate this with respect to x? Do I want to integrate with respect to y? What's the easiest? Which one's going to potentially give me the fewest amount of integrals that I'm going to have to write? So if I wanted to integrate this with respect to x, that means I'd be accumulating area in this direction like this. So I'm going to have a couple things that I'm going to have to notice here, right? So at x equals -1, we have a change in the top versus bottom function. So in this one, the top is this part of the blue function, the bottom is this part of the blue function. So first of all, we'd have to have 2 different equations for this function. And then it changes here at the right of x equals -1. So then we would have this blue function and then this red function. So that would be if we were integrating with respect to x. But if we integrate with respect to y, notice that if we do right minus left, it's always on this whole region going to be the red function minus the blue function. So maybe integrating with respect to y is the best way to go. Is there any way to nicely do this with respect to using geometry? I don't really think so. So I think we want to integrate this with respect to y. So we're going to do an integral with respect to y, which means all of my equations have to be in terms of y. So let's go ahead and do that. So if I want to isolate x here, I'd have to take the cube root. So this is going to be x equals the cube root of y. This one's already solved for x, so that's good. This cubic is our top function, or the right function, and then this is our left function. So it's going to go the integral. So it's right minus left, so it's going to be cube root of y minus the left, which is y squared minus 2. And then integrating with respect to y. Now, where are we going from? So we're going to be starting here and going to here. So we're using the y value. So it's going from b to d, from b to d. And this would be your integral that you'd be using. If you wanted to simplify this, you could. You'd say it's the integral from b to d, distribute the negative through. I would probably change this to be an exponent, so y to the 1/3 minus y squared plus 2, then with respect to y. And that would be the integral that I would evaluate to find this area here.